Today we're going to look at several other bus-based coherence protocols. Let's take a look first at the MESI protocol. As shown in the table at the lower right of the slide, it is a four-state invalidation protocol. With your knowledge of the MSI protocol, perhaps you can answer this question. If a line is in state M and the snooper notices a bus read to that line, which state should it change to, S or I? The MSI protocol moves it to state S. And that's a good choice if the processor whose access is being downgraded will reread that line soon. It won't have to refetch the data if it references it again. So it is good for data that is read a lot more often than it's written. But suppose the data is read and updated by a lot of processors. This would be the case, for example, if a group of processors are adding to a global sum. In this case, it would be better if the line state were set to I. This would save a bus read X and an invalidation when the next processor writes the line. Here's another way we might tweak the MSI protocol. If a processor reads the value of a variable and then writes it, two bus transactions occur, a bus read and then a bus read X or a bus upgrade depending on the protocol. This happens even if the line is unshared, and most of the lines in most caches are unshared. This means that even single-threaded programs induce bus transactions and potentially slow down other processes. To avoid this, we can add a fourth state to the protocol. This is the exclusive state, or state E. This means that the line is clean, but only one processor has it cached. The shared state still means that the line is clean, but in the case of a shared line, there may be copies of the line in two or more caches. This raises a question. When a clean block is fetched from memory, how does the protocol decide whether it should go into state E or state S? It does so by checking whether another processor has a copy of the block cached. This is done by observing whether a so-called shared line is asserted. When loading a block, this line will be asserted if some other cache already has the block cached. So our transition diagram now has four states, M, E, S, and I. If a line that was not cached or was invalidated is fetched into the cache via a processor read, the ensuing bus read checks the shared line. If it's not asserted, the line is cached in state E. However, if the line is asserted when a block is fetched into the cache, then the line changes into state S. And if the miss is a write reference, the line is cached in state M. If a line is in state E and is read, then it stays in state E and no bus transaction is necessary. But if it is written, it has to change to state M. Note that no bus transaction is needed. This is the strength of the MESI protocol. If a line is in state S and is read, then it stays in state S and no bus transaction is necessary. Now see if you can fill in the last two transitions. One of them is if a line is in state M, then it can be read or written without any bus traffic. The other one is if a line is in state S when a processor writes to it. This means a processor is writing to a clean block it already has cached. Now let's look at the bus-initiated transitions. If a line is in invalid state and another processor reads or writes it, it stays invalid. If a block is in state E when a bus read comes in, that means another processor wants to cache it, so the block will now be shared. This requires a transition to state S. If a block is in state E when another processor writes it, it must transition to state I. But this processor holds the only valid copy of the block, so as it is invalidating it, it sends it out onto the bus from which main memory, as well as the requesting processor, pick it up. If a line is in state S and another processor reads it, it stays in state S. In this situation, some protocols supply the block from memory, others depend on the processor to send the data. If the protocol is a cache-to-cache sharing protocol, it is the cache's responsibility to do the flush. So it flushes the line onto the bus where it's picked up by the requesting processor. The prime after flush indicates that this is only done in a cache-to-cache sharing protocol. If a line is in state S when a bus read X comes in, it transitions to state I. And if cache-to-cache sharing is in use, it's the processor's responsibility to put the line out on the bus. If a line is in state M when another processor reads the line, it transitions to state S. Note that in this case, the processor always flushes the line because only the processor in state M has an up-to-date copy of the line. But if a bus read X comes in while the line is in state M, it transitions to state I while flushing the block. Putting it all together, we see that the M state is at the top, representing the most control by the owning cache. The E state is next because it can transition to M without a bus transaction. S is next, and I is again at the bottom. The edges on the left side of the diagram represent processor-initiated transactions, and the edges on the right side represent bus-initiated transactions. When our animation starts, all caches are empty, and the value of A in main memory is 1. Processor P1 reads A, but A is not yet cached. This induces a bus read transaction. The memory controller responds with a block. The block reaches P1's cache. The state of the line is set to E since the line has not been modified and is not held in any other cache. This completes the read operation. P1 then writes A, changing its value to 2. This is a cache hit, but the cache has to change state to M. No bus transaction is needed because a block in state E can't be held in any other cache. The write operation is now complete. Now P3 tries to read A. This causes a cache miss, so a bus read is issued. P1 snoops the read and changes its state to S. P1 flushes the block across the bus where it is picked up by main memory in P3. Then the read operation completes. Next, P3 writes A. Because its copy of A is in state S, it can't write it without issuing a bus upgrade. Or, if there's no bus upgrade, it would issue a bus read X. The bus upgrade is snooped by P1, which has to invalidate its copy of A. Meanwhile, P3's write completes, changing the cached value to 3. P3 changes the line state to M, and the write operation completes. Now P1 tries to read the value of A from its cache. But since its copy is invalid, it needs to issue a bus read to read it. P3 snoops this bus read and flushes the block out over the bus where it is picked up by memory in P1's cache. The read operation completes. Now P3 reads A from its cache. This is a cache hit, so the cache simply returns the data. No bus transaction takes place. The read operation completes. Now P2 finally gets into the act by issuing a read for A. Since it's a cache miss, it requires a bus transaction, namely a bus read. P1 flushes the block out on the bus, where P2 picks it up. This is referred to as a cache-to-cache transfer. The read operation is complete. Now all three caches have valid copies of the block in state S. This table shows which caches have the block in which state after each instruction. It also shows which bus action takes place. We've assumed that when a line changes from state S to state M, a bus read X is issued. But our system might also support a bus upgrade transaction, in which case the line can change to state M without the block having to be sent across the bus to the requesting processor. Also notice where the data comes from. It comes from a cache, except in two cases. The first, read from memory, when the block changes from state S to state M. In the latter case, if bus upgrade were used, data would come from the cache. But if there were no cache-to-cache transfer, data would have to come from memory on the last read. Now let's take a look at how this protocol differs from MSI. One obvious difference is that processor 1 caches the block in state E. Then, when P1 writes the block, the state can change to M without a bus transaction or a read from memory. The last difference is due to the cache-to-cache transfer. Instead of a bus read and memory supplying the data, there's a bus read and a flush from another cache. If bus upgrade is used, there's only one other difference. When P3 writes to the cache, the bus upgrade is used, and data comes from P3's cache instead of from main memory. As we've seen, cache-to-cache transfers are used in this protocol. But cache-to-cache transfers add complexity because memory can't respond with data until it's sure that the caches won't. And if multiple caches have valid copies of the block, as occurred during the last step of our example, the caches must agree on which of them is going to flush the data. Cache-to-cache transfers are useful in a distributed system if the cache is in another processor at the same node and the memory is at a different node.